Before I get started, please subscribe to this channel so you don't miss out on any new material that I'm going to be producing in the future. And that helps us grow the channel, grow more content, and help people like you. Well, I appreciate everybody being here this evening. I know it's late for, I think about, 7 p.m. where you are right now. So I appreciate that. This talk is going to take a little bit over an hour. I can't get it any shorter and present enough of the draft design where you can have a really good, strong understanding of where this is going. So this talk is trying to present to you the current draft syntax proposal, where we are today. Right now, it seems like the language team and the community are pretty happy with where we're at, and which I'm going to show you. But you're going to have an opportunity also to participate in that conversation. Actually, Eric, I'm going to send some links to you over Slack. Can you drop them in the chat for everybody? That will be appreciated. These three right there. A couple of ground rules here as we get started. Eric's dropping some links into the chat window. I'm not going to really be able to take questions during the talk. So what I'd like is everybody really participating in that chat area in Zoom. Have as many conversations as you want. And help each other out through the course of the talk. Once the talk is over, we're a small group here. I'd like to get feedback from everybody. So we'll open it up to give everybody a turn to talk for 2 or 3 minutes after the talk. Okay. So, and a lot of times I'm answering questions by the time I'm through as well. But if you ask questions on chat, maybe somebody has an answer already for you. I'm going to try to present the draft syntax. That's all we have right now. We've been exploring and experimenting and prototyping with what a syntax could look like for generics. It's important that you understand that there is no compiler implementation of this as of yet, though the Go team has started some preliminary work on that. I think it was this week. So they're feeling more and more confident that that the syntax I'm going to present to you is probably where we're going to end up. The other thing here is when could we expect, if at all, a version of this in the compiler? The language team is telling me that if everything goes perfect between now and August release of next year, which will be version 1.17, we could potentially see a compiler implementation. That would be the earliest, version 1.17, August. Though if I was a betting person, I would say the 1.18 February release of 22. But you never know. We'll see how it goes. There's more community discussions that have to take place. Now, I asked Eric to drop 3 links into that chat. The first link is where the training material is. I'm going to be showing you that in a second. The second link is a link to the draft document. And the third link is a link that points to a form to be able to provide anonymous feedback to the Go team that is working on this. So that's your opportunity to participate in the conversation without getting it into that public, the mailing list and issues and things like that. So I hope you take advantage of that. Okay. I think with all that said, it's on my side, it's 2:10. I think that means it's 7:10 on your side. Eric, switch over to my machine here. I'm going to switch over to do the repo. I've got the font a little higher so we can see things a little bit better. This is the Go training repo. I know it's a tad blurry. Zoom never gives me high def video for some reason. But you can see here there are 13 different examples. We cannot go through 13 of these. We just don't have the time. I'm only going to get through the first 5. If I get through the first 5, you will have seen a really good, maybe 80–85% of what's being discussed in the draft document. The rest of these examples I'll leave up to you to look at on your own. There's a README. In the README, you'll find a link here that will also take you to the draft document. You can see it's been updated as early as 3 days ago. Now, you don't necessarily have to read this. The whole point of this talk is so I can kind of go through what's here without you having to sit and read it. If you have read it, that's great. There's also a go-to-go playground that lets you explore and experiment with the syntax. This is completely up to date. We won't be using this. I'll be running it locally. But throughout the course of the talk, if you've got some code that you want to share with me at the end of the talk, you can put it in here and hit that share button and give me a link, and then we can kind of discuss it as well. So the go-to-go playground is awesome. Again, just remember that this go-to-go is not a compiler implementation, but a transpiler tool that will convert the new syntax into existing syntax so it can build and run. Now, I'm not going to read this list, but this is the things that are currently being explored and prototyped as a first release of generics. It doesn't mean that this won't make it into Go in the following releases, 18, 19, 20, 21. It just means that right now this is what's being focused on as an initial implementation and for syntax. So you can read that on your own. I don't need to read it. If you're wondering if any of these things are going to be in the first release, the answer right now is no. I don't expect any of this, like metaprogramming, to get into the first release of generics for Go. It doesn't mean, again, that it may not make it in, but I won't be showing you anything related to this list right now because it's just not being worked on. There are some extra links in here for reading if you want to go deeper. I'm writing different blog posts for the different examples. And if you do want to play with the go-to-go tooling locally, there is instructions here on how to do that. And that's exactly what I'm doing right now. If I go over to my terminal window here, type Go version, you'll see that I'm not running 1.15.2. I'm running a version back from source on the 15th, which is, I think, about 9 days ago. So that's where we are right there. OK. With all that being said, it's now 1/4 after the hour. I expect to be done at around the same time next hour. A lot to cover, so we're going to get to it. And I'm going to do that using the VS Code environment that I have. And we're going to start with this very first example here. Let's see if I can work with it. It's a little too big for me. I'm going to go a little lower. I think that's OK on the resolution. If at any time during the talk you can't hear me, you can't see something, something seems to be technically going wrong, please just type something in the chat window to let us know. I can see the chat. I can see what you see. And Eric is available to help us with any issues there. OK. Let's learn the new syntax being proposed for generics. And also, let's understand why we even need a new syntax. I think that is as important as anything else. So on line 13, I'm going to start with what I call a concrete function. I call it a concrete function because this is a function that's asking for data based on what it is. And anytime we have a function asking for data based on what it is, we're really limited to just asking for that one type of data, that one type of concrete data. And this print numbers function is asking for just a slice of integers, a collection of integers in Go. Now, if you look at the code we're writing for this print numbers function, it's 5 lines of code, where in line 14 we print a header, on line 18 we do a carriage return and line feed. But in the middle of that, we're doing a linear traversal using our language mechanics and syntax, the 4 range mechanics, there they are, where we get to iterate over each number in the collection, and then we print that number, and we can see them all. 5 lines of code, there it is, to display individually each number in that collection. Now I'm going to make a big, bold statement here and say that I believe that almost all Go developers, even those that are only maybe a week or so into the language, can read and comprehend the code I just wrote for print numbers. I think it's one of the things that we love about Go, that Go is really not trying to be novel in terms of syntax and language mechanics. That if you're a software developer, maybe if you've never even seen Go before, but if you're a software developer, you can read those 5 lines of code and understand it. And what I want to focus on in this talk, and what I want the community to focus on here, is not will generics allow us to write code that can perform faster than what we have today, but can we write code that will give us higher levels of readability and comprehension for the average developers that are working on our team? Because if the answer is no, then I want nothing to do with generics. This has to give us the ability to write code with that same or higher levels of readability, comprehension, with the ability to also reduce maintenance costs, right? Because that's going to be a big thing. I'm going to focus on all of those as we go. Now, I've got this print numbers function. I've made an argument that everybody can read this fairly quickly, even if you don't know Go syntax. It's kind of obvious. But if I wanted to now do the same thing for a collection of strings, because these are concrete functions, I now have to write an entirely new function. And that's what you see on line 21, right? You see me writing a new function called print strings that now takes a collection or slice of string. And we can all look at the 5 lines of code here between lines 22 and 26 and say, Bill, that's essentially the same code. The only difference is the variables are changing to be in context with the data type, and I've changed the header. But mechanically, it's the same code, right? Now, if I wanted to do this with floats, what's going to happen? I got to write another function. Now, I could make the argument that writing another function for each of these can add some value, because if this function, print numbers, has a high level of readability and comprehension, then so does print strings, and so would print float and print user, and that's going to help a lot with maintainability, right? Well, I think the cost of that, the cost is going to be what? We're going to have a lot of functions and a lot of code that we have to maintain. And potentially, if we find a bug in one of these functions, we're probably going to find the same bug in all the others. And so even though our readability and our comprehension of this code is high, the maintainability cost here is high too, right? The cost is high. It's harder. And so when I think about the problem that I have in front of me, thinking about the current language that we work with today, our language syntax and mechanics for 115, I ask myself, well, is there a way to write this code where we can consolidate it all in one function to help reduce the complexity and maintainability, but still maintain that high level of readability? And when I think about that, I do come up with an answer right here, which on line 35 is my print assert function. And the idea of this function is a way of consolidating at least those 2 other functions into one function to help with the maintainability, right? I have to maintain 2, 3, 4 functions. I maintain 1. But to get this to work, I can't be using a concrete function anymore. I need essentially to write a polymorphic function. What do I mean by that? A polymorphic function doesn't ask for data based on what it is. A polymorphic function asks for data based on what it can do. That's the idea. That allows us to pass different types of concrete data through the function based on the fact that all of that data can do the same thing. Now, in this particular case, I don't particularly care what the data can do. And so you see the use of the empty interface. Now, the problem with the empty interface is it does allow us to write a polymorphic function, but it doesn't describe anything about the data. We're really blind. But in this particular case, this is the only way to do it, because I want to be able to pass a slice of int or a slice of string, and that empty interface allows me to do that. But once we come into the function, v, the interface value, is abstracting the concrete data, and since there's no behavior behind it, we need to inspect what's inside the interface. Now there's a couple of mechanics to do that in Go, and what you're seeing here is the use on line 37 of the type assertion. A type assertion let us at runtime inspect what concrete data is sitting inside of that interface, which is decoupling us from the concrete data. And you're seeing also the use of a generic type assertion using the keyword type and the switch statement. So this is a generic type assertion as well, where we're going to use each case to determine conditional logic for what is inside of V. And if there is a slice of integer inside of V, we'll execute that code. If not, we'll execute this code. And so we've consolidated this, but a couple of things here, right? This really isn't a generic function, because if I pass a slice of anything else through, we're not going to see an output. We can only output here what we code. And two, the code on lines 39 through 41, again, mechanically is the same as 43 through 45. The only thing we're changing is the variable name just to have some context. So we do maintain, I would argue, a high level of readability and comprehension because we're using our language syntax and mechanics. We have gained some maintainability because we've got just one function, but there's still an ounce of code duplication here that isn't necessarily great. So then I ask myself the following question. Well, in the current version of Go right now, 1.15, is there a way to write this print function in a generic way, where I don't have to worry about multiple implementations? I can write just one implementation with one function, and then I'm set. And the funny thing is, the answer to that question actually is yes. Here it is, right there on line 56. I call this function print reflect. And once again, we use the empty interface to be able to accept concrete data based on what it can do. And in this case, I don't really care what it can do. So we could pass any sort of concrete data we want. But if you just stare at the 8 lines of code that I wrote there, I think you're going to start to realize that you don't see a lot in terms of language syntax or mechanics. And that's because to write this generic version of print, I have to use an API. I have to use the reflect package from the standard library. This implementation is API-based, not necessarily language syntax-based. And you can see what's going to happen here on line 58. We do our value of call, so we can get a reflect value that gives us the ability to inspect at runtime what's going on with the concrete data stored inside of V. And then I can use the method set of val in many different ways. I can ask, well, what kind of data stored inside of V? Because if it's not a slice, we're done. The whole point here is to print a collection of values. I can do this at runtime, and there it is. Now, I can't use my language mechanics and syntax, right? But I do have to do the linear traversal. So what you see me doing on line 62 is incrementing a local variable I through length. I can't use the built-in function len, but I can use the method. And then I can go ahead and do my linear traversal again using another method called index. An interface gets me back to the data, and then I can just display it all on my print. This is truly a generic function. This can print a collection of ints or floats or users or anything. And really, it's capable of doing that because the print function from the front package is also using reflection underneath. That print function uses reflection to determine a default output for any sort of data value that we pass into it. And so here we see the use of reflection in 2 cases, one in that print, and 2 in our ability to inspect at runtime the data. And we see the use of a polymorphic function to accept any concrete data we need in this case, and it doesn't have to behave. But I can't make the same argument I made before. These 8 lines of code are not as readable. They're not going to be as comprehensive as what we saw before. The average developer on our team and anybody brand new to Go isn't going to necessarily understand this code just by looking at it. You need to understand the API. And so though maybe we have some maintainability gain here because it's one function and 8 lines of code to do it all, we are losing readability. Right? We are. We're not going to, this code isn't going to be as readable to as many Go developers as the other version. And so now I get to this final question. Is there value in being able to write code with our language syntax and mechanics and still have the ability to just maintain one function? And I think the answer is yes. And can this new generic syntax give us that? And I think the answer is yes as well. So what I want to do now is show you, based on the draft syntax that we're currently exploring, what a generic version of print could look like outside the use of the reflect package. Now I want you to just focus here on lines 82 through 86 to begin with. Because if you notice, it is the same exact 5 lines of code that I started this talk with. It's the same 5 lines of code we used when we were working with a slice of int or a slice of string, and it would be the same 5 lines of code if I wanted to work with floats and users. We're back to using language syntax and mechanics, and this is because we're back to really writing a concrete function. It's no longer a polymorphic function. We're writing a concrete function. Well, it's interesting because this is a concrete function where we want to be able to, at compile time, where we want to be able to determine later what the actual concrete type is. And sometimes that's called parametric, right? Parametric, polymorphism. It's a different kind of polymorphism. It's at the compiler level instead of what we were seeing in our traditional polymorphic functions, right? Say at runtime. So I want to explore here a little bit of the new syntax, because to get this to work, we needed some new syntax. But to do that, I'm going to remove the new syntax first. So we can look at this function as if it's just a regular Go function that we're used to writing today. Now, you know what I'm trying to do here, right? I'm trying to say that I want to write a function named print that accepts a slice of t, but not really t, but a type to be determined later. The whole point is I want t to be substituted for something later, but write the code now as if t is something concrete like an int or a float or a user. The problem with this syntax that we have here that I've written is that this syntax assumes that somebody somewhere before we hit the build button is going to be declaring t. This syntax that we have today assumes that t will be declared and will be identified before we hit build. Boom, there it is. There's t. Life is good. And this is really quite the opposite of what we want, right? The whole point of what we're trying to do here is say that t isn't going to be declared before I hit the build button, and that this t needs to be identified later, potentially at compile time. And this is why we need a new syntax, because what we've got to do is tell the compiler, don't look for t, at least not right now. We want t to be identified as a generic type. So we need a syntax that tells the compiler that t will be a generic type. How do we do that? Well, in the current draft, the syntax that seems to be holding pretty strong is to use a set of square brackets to define a list of generic type identifiers. A list. It doesn't just have to be one. I mean, it could be many. But this is where we're going to declare that t is a generic type. But in order to make sure that the compiler never confuses this with an array anywhere within the scope of the syntax, the spec says that all generic types must have declared with them a constraint. And when there is going to be no constraint associated with the type, we are to use the pre-declared identifier any, which to me represents anything. In other words, what we're saying now is T is a generic type to be determined later, and it can be substituted for anything. That's what we're doing. The last two examples in this talk, I will talk about constraints. For now, with what I'm going to be showing you, when I apply the constraint, it will be any, representing that T can be substituted for anything. And now we have the new syntax. And the purpose behind it is to tell the compiler that T is not some concrete type it should expect to see being declared somewhere in some file, but T represents a generic type to be determined later. And now, since T represents a concrete type, we get to write code as if it is. And we get back to our language syntax and mechanics. And now we're back to 5 lines of code that everybody can read and comprehend and understand. And we gain the benefit of maintenance because this is the only implementation we need. There it is. Beautiful. Now let's run this code here. And so in main, I'm going to construct a slice of integers on line 92. I'm going to construct that slice of strings on line 98, and then pass that slice across the 4 functions that can accept it, and pass that slice of strings across those 4 functions. And if I come into my terminal here, and we change into the first function example, we can run this code. Now, remember, there is no compiler implementation yet, so I can't just say go run. It doesn't exist yet. But I can call out to the go transpiler, since it is a tool that's accessible in this version of Go that I have from the front end. And then I can say run and provide it the go-to source code file. What will happen is the go transpiler will convert this into a Go program that is capable of being built and run with a bunch of interesting support functions underneath. But if I hit enter on this, we now see the output. And we see here that our reflect and our generic and all the other functions have the same output. And what is the big win here? What are we really trying to accomplish here? With the readability, higher levels of code comprehension, and maintainability? Well, this, right? Isn't this the big win? The ability to say, I'm going to have a set of floats, which are going to be a float 64, and just apply a couple decimal points here like this. And then be able to take our 2 generic versions of this code. Remember, reflect is as generic as print. It's just this is API based. This is language syntax based. So I should be able to build and run this code. Let's see. There it is. And so we now see, without an extra implementation, that I'm now able to display floating point numbers using my reflect and my generic functions. OK. Now, there's a couple more things here that I do have to talk about. A big part of the compiler implementation is to make this usable. And to make it usable, what's going to have to happen is that the compiler, when it's capable of doing so, wants to and really should need to infer what type T is going to be. You heard me say that T is to be determined later. Sometimes T can be determined at compile time if it can infer that type based on the call site or the construction site. what we're seeing right now is the compiler figuring out what t is at the call site because of the way the code is constructed and the fact that I'm passing in a slice of int, a slice of float, and a slice of string. So when t is being used as an argument for input, this lends itself to the compiler being able to infer the type. This is beautiful. So if I pass in numbers and the compiler sees this as a slice of int, then the compiler can assume that we're substituting t for an int, and then compile and build the code. Being able to infer the type at compile time is beautiful. But what if t wasn't being used as an input argument? It's just being used somewhere within the implementation of the function. Now there's nothing for the compiler to leverage to infer. So how do we determine what t is later if it can't be done necessarily at compile time? Well, we have the ability to pass the type information in using the same square bracket syntax. In other words, these parentheses represent data we can pass in. These parentheses also represent type information that we can pass in, though we would prefer not to have to do that if the compiler can infer the type at compile time. So we're not just declaring, right, a generic type to be determined at compile time. This list can also be used as a way of passing that information in. So I can say here, float 64. I can explicitly pass int here. The compiler doesn't have to worry about trying to infer what type t is, and then it can guarantee that it matches the data input on that call site. So I want you to understand that when I say to determine later, type t to be determined later, that could mean that it's determined at compile time by trying to infer the type based on, say, data input. Or it might mean that we have to explicitly tell the compiler what t is going to be because it can't infer it by itself. But in the cases where it can, it's beautiful because calling a generic function looks and feels no different than calling any other function. OK, great. Now, we've looked at generic functions here. And that's great. But, you know, one of the things that I teach, that I hold true to, is that Go is a data-oriented design programming language. In other words, what data-oriented design says is every problem that you solve is a data problem. Every problem you solve is a data transformation problem. There's some input, you transform it, there's some output. And so if you don't understand the data, you don't understand the problem. If you don't understand the problem, why are you writing any code? I mean, Rob Pike, and I'm paraphrasing, said that if you're able to define your data structures the right way, the algorithms are self-evident. In other words, we start with the data. We start with our data models. We start with our data structures in the concrete. And other things should be discoverable. The algorithms should be self-evident. So we're going to be defining lots of user-defined types in the software that we write. And generics are going to play a role in that. Now, there's two ways of defining a user-defined type in Go. We can define a new type based on an underlying type, or we can define a type based on a struct type. So I want to present both of these to you. Let's start with an underlying type. OK, let's get to the beginning of this code. So you see here on line 15, I'm declaring a type named vector int that has an underlying type of a slice of int, which really means that this vector int is a slice, right? Like its data model is a slice. There on line 24, I'm defining a new type named vector string whose underlying type is a slice of string. That's what it is. It's a slice of string. Now, if I wanted a vector of floats, as you know, I'm going to have to define another type. But to make this example more interesting, on line 17 and 26, I added a method to this type called last. What last does is return the last value in the vector, which is the value at the highest index position. Now, the last implementation for vector int has to return an int, because that's the kind of data we're storing. The last implementation for vector string has to return a string, because that's the kind of data that we're storing. And you can see that the 4 lines of code here really match the 4 lines of code here. And if we walk through it, what we'll see is that we're checking to see if the vector is empty. And if it is, we return an error, and then the 0 value for an int, which is the idiom in the guideline that we follow and teach in the community. If you're returning an error, then return the 0 value construction for all those other types. We tend to do that directly on the return. If it's not empty, then we return the value, the integer value, the highest index position, and nil, which is the 0 value for the error interface. Now, the implementation of last is identical except for one thing. The 0 value for a string is not 0. It's an empty string. But it's OK. We hard code that right there in the return, and life is good. OK. So I've got these 2 implementations of a vector. And again, if I wanted one that works with floats or users, I'd have another implementation. We're back to the high level of readability, but the lower level of maintainability. Now, the question is, can I do this in a generic way today in Go? I can. On line 40, I can change the vector out to have an underlying type that is a slice of the empty interface. We're back to polymorphism again, right? But polymorphic behavior that really describes no behavior. So we're kind of blind again. And you can see the implementation of last is the same 4 lines of code where we're returning nil for the 0 value of an interface, because that's what that is. Now, the same 4 lines of code apply. We could argue that the readability in this case really didn't change. But I'm going to make an argument that the usability has changed. There's one big semantic change between this vector and the others that I showed before. The others that I showed before were restricted to one type of data. So when we called last, we knew what we were getting back. But we can intermix different types of data in this vector, which means that when I call last, I really don't know what I'm getting back. I'm blind. I'm getting back an interface value that has a concrete value in it of some unknown type, which means from a usability perspective, I'm back to having to do type assertions or reflection to know more to then write whatever business logic I need to write. So there are some semantic and usability changes here. What I really want is a generic implementation of a vector that is restricted to a single type of data, so I can get my readability and my maintainability, and in this case, my usability, right? And so here we are again with our generic implementation of vector. Throughout this talk, I'm going to remove parts of the new syntax, because I don't know about you, but my brain is more wired into looking at code without it, and then applying it in makes it easier. Look, you know what I'm trying to do on line 56, right? I'm trying to tell the compiler I would like to declare a vector that has an underlying type of a slice of some type t to be determined later. That's the whole point. Not actually t, but some type t to be determined later. As soon as I say some type t to be determined later, what do we know? Well, that's a generic type. What do we know? We need some square brackets to help declare the generic type identifier, and we need the constraint of any to, again, represent that there is no constraint on what t can be substituted for. OK, great. So now I have my vector type, which is leveraging a generic type identifier to declare what the underlying type is, a t, some type t to be determined later. Now let's take a look at the last method, because since this is a method, it's going to be bound to the type through the receiver. Since this is a method bound to the type through the receiver, we'll never see another type list like we saw with a generic function, because that syntax is already being applied to here on the declaration of the vector. But look at the receiver. You see that I'm using value semantics. This is a value receiver. There's no pointer here. It is a value of type vector. But remember, vector by itself doesn't mean anything, because we've got to tell the compiler at any point in any sort of construction syntax or declaration syntax the fact that what the underlying type is going to be. And so anytime we use the identifier vector, it's never going to be enough without the use of the square brackets and some type information. But since we don't know what the type information is here because we're declaring a method, we're going to use t as well. And we're saying that this method is bound to a vector of some type t that ends up being determined later, whether at compile time or explicitly. What's also nice is that we're returning a value of type t as well to be compliant with the way the API works. If we're storing integers, we've got to return int. If we're storing strings, we've got to return strings, users, users. Now, what I love about this is we're back to those same 4 lines of code, right? The same language syntax and mechanics that we've been using. And this implementation is bound to a single type. We get readability. We get better comprehension. We get maintainability. There we are. Now, let's follow the code here. We're going to check to see if it's empty. If it's not, we return the value of type t in the largest index position that is there, and nil for an error. But if it is empty, then we return the error, and now we have a problem. Because I want to return the 0 value of t. In order to do that, we need a universal way of being able to construct a value of t to its 0 value state. Everybody's first initial reaction to this is to do this. Is to construct t using empty literal syntax. Notice the words I'm saying, empty literal syntax. Why not just use empty literal syntax to construct a value of type t to its 0 value state on the return, Bill? Well, look, if t was substituted for a struct type named user, that would work. It would. It would work. But t was substituted to be an int, that syntax isn't valid. It doesn't even make sense. We can't construct an int using empty literal construction. No, I mean, it doesn't work. And so not all types work with that syntax. So we need a construction syntax that works for all types. Now, the language has 2 of them, believe it or not. The first one, and the one I prefer, is what I'm showing you on line 59. And that's using the keyword var, which is why in all of my classes I always teach, use var, not empty literal construction for 0 value, because it is a universal way of constructing any type t to its 0 value state. And just remember, as a side note, if you use empty literal construction on a slice, you don't get 0 value, you get an empty slice. And so what I like about this solution is regardless of what t is, whether it's a user, whether it's a string, whether it's an int, whether it's a slice, it all results in the same thing, 0 value construction. And then what we can do is use that variable on the return, which I think gives us higher levels of readability in terms of we're returning the 0 value for that type T. This is the solution I like. Now, there is a solution that would eliminate that line of code. The other universal way to construct any type to its 0 value state is using the built-in function new. New constructs a value to its 0 value state. However, new uses pointer semantics and will return the address of T. And so to be compliant with the type information, we would have to dereference that pointer back to the value that the pointer points to, which to me has lots of data semantic issues if you take any of my classes. But more importantly, I don't believe that that code is as readable and will be as comprehensive, right, comprehensible to as many Go developers as the other syntax. We did get rid of a line of code. I potentially made something easier to do. But did I make it easier to understand? My argument is no. More Go developers, especially those new to the language, will understand this syntax much more than they will understand the dereferencing of a call to new. They both work. They both result in the same thing. But I think data semantic-wise, I think reading-wise, comprehending-wise, this is a better solution. OK. So we now have our vector defined. Here it is. And I want to see how this now works. So if I go into main, I start with the construction of our vector int and vector string, which were bound to a specific underlying type. But remember, the beauty of these vectors was when I call last, I know I get an integer, which means I can provide some sort of extra logic without any sort of usability issues. I know I'm getting an int. Is it negative? On this call to last, I know I'm getting a string. Is it valid? I can do that. The problem is if I need to apply the same sort of logic, and we work with the interface using the vector using the empty interface, I have my usability back. Because look, there's nothing stopping me from storing different types of data in this one vector. Now when I call last, I don't immediately know what type of data I have. I have to go back to reflection, or in this case, a generic type assertion. And then, and only then, can I apply the right logic. So I feel like this solution lends itself to misuse and fraud and usability issues, which is why I love the idea of our generic vector. So on line 107, you see me constructing a vector. I'm specifying that T will be an integer. And then I'm using literal construction to initialize that vector at construction time. What's beautiful is since T is an int, we know that last returns an int. And I'm back to being able to do any sort of processing. But using the same vector declaration, I can now specify that T is a string. And using that literal construction, put some strings into the vector. And then we know last is returning a string. And there we are. And if I were to just build and run this code for a second, we see down here that that same vector implementation is now being used for ints and strings. And what's the big win again? What is the big win, right? The big win is that from an application standpoint, I can do this, right? And now just start working with any other type that I want. Maybe we'll just call this a float. We know that this now returns a float, right? Which means I can even do negative processing if I want. It's a negative float. And what's also cool is I can use the specific verb for float inside that print statement because I know what type of data I'm working with. And if I did everything right, we're now working with a vector of type float. Now, one question you might be asking is this. separate this for a second. Bill, why are you passing the integer information explicitly when you're using literal construction? Can't the compiler figure out, based on the values that are part of the literal construction, that this vector should be working with an integer? Well, the answer to that question is actually yes, it can. And then, Bill, why is it not working? You may run into situations right now where certain things are supported by the draft, but they're just not implemented yet, and probably won't be implemented, because why spend time on something that isn't that critical in terms of getting to a design that will eventually get into the compiler? So in a compiler implementation, this will work, absolutely. The compiler will have enough information to be able to determine the type, just like this. It would have enough information. I'm just letting you know that right now, the current Go tooling isn't supporting it because it hasn't been implemented for no other reason than there are more important things to be spending time on. But if you were to be constructing a vector to its zero value state, you'd have no choice but to explicitly pass it. So again, anytime I talk about t to be determined later, if it can be determined through, if the compiler can infer the type, then t can be determined at compile time. If the compiler can't infer the type, then t has to be determined at the construction or the call site by explicitly passing that information. OK, brilliant. So we've seen now the use of this syntax as it relates to a user-defined type, leveraging an underlying type. You got to see the implementation of a method where we needed to be able to return a value of that generic type t. And we focused a little bit on the options you have for doing zero-value construction. Now, I don't know about you, but probably in the 7 years that I've been coding in Go, I haven't declared a lot of user-defined types using an underlying type. I haven't done that much. But struct types are very, very, very common. So I want to share with you how we could leverage generics with a struct type. And then this plays into the idea that we can have fields in a struct that are based on that generic type t. So if you look on line 16, once again, I want to define a node for a linked list. These struct types are going to be really valuable for these, what they call these container types, right? These linked lists and trees and hash maps and all that other good stuff that we have. So once again, the idea is that I want to define a node that can store a value of some type t. Now again, since t needs to be a generic type, you're going to see me apply the square bracket to define this as a generic type. And again, there is no constraint on what t can be substituted for, so we're going to say it can be anything. And now we can define data to be a field of some type t to be determined later. Now, this is a linked list, and it's a double linked list, so every node can point to the next node or the previous node. That's going to be pointer semantics. But it has to be a node of the same type t. So just like you saw with the receiver, anytime we're going to reference node, the type, we've got to reference it with the type information for the generic type identifier. In this case, we don't know what it is just yet, but we do know that t is going to be the substitution for it. And so what we're going to say is that next and previous point to another node of the same type t. There it is. Now, if you look on line 22, we have a list. And that list contains the first and last pointers to our list. And once again, because we've got to have pointers to a node, it needs to be a node of some type t. So we go ahead and declare that generic type list again, saying that t is a generic type for this type. It can be anything, and then we can apply that to our first and last nodes. Now to make this more interesting, there's a method named add. Now again, it's bound to the list type, this time using pointer semantics. Once again, you can't construct a list without knowing what T is. So we now use that square brackets. And we define add to be able to accept a value of type T and then return a node. But again, it can't just be a node. It's got to be a node, in this case, of the same type T that we're using to construct the list, which is the same type T we're using to pass data. Let's look at the implementation of add. Because again, what generics is trying to give us is better readability, is, again, higher levels of comprehension, but also the maintainability by being able to have just one implementation of something. All three of these things really need to come together for generics to be, I think, a viable solution. Now, if you look at the basically the 11 codes, the 11 lines of code that I wrote here, you can see here that these lines of code don't change regardless of what the data is that we're storing in a node. This is what makes these container types so miserable to have multiple different implementations for different data types. Because the bulk of the code is the same, right? It's the same. The only thing that's changing is the construction of a node, because the construction of a node has to be of some type T that is being determined later. So we can assign that data of that type T to the right field, and we can have pointers of a node of that same type T to the previous field. Right? This is the big win. This is the maintainability win that we're going to get. So there it is. We see an add method. Now, let's just play with this for a couple of seconds. On line 46, I'm declaring a type named user. That's the data that we're going to be storing in our list. And then on line 55, you see zero value construction, var, of a list, where we have to explicitly tell the compiler that T will be of type user, because there's nothing that can be inferred here. To be determined later is being explicitly provided. But because we are using user for type T, add now accepts values of type user, and data will be values of type user. But remember, we can substitute T for any type and any data semantic. So here we're constructing a list also set to its zero value state. But instead of user values, we're saying pointers to user addresses of type user, which means add now only accepts addresses of type user, and data will be an address of type user. And we can see that if we go ahead and run the example for 3. You see that FUMPT is telling us ampersand or no ampersand. Pretty cool. And there's some intuitiveness here around the API, because if I construct a list where T is of type user, then everything is going to be value semantic based. If I pass pointer semantics here, then everything is pointer semantic based. Now, one thing I just want to make you aware of is that you may have situations where you don't want T or T in the implementation can't be using value semantics. Maybe the data can't be copied, and that becomes a dangerous situation. There's nothing stopping you from going into your implementation and forcing pointer semantics, say, on that data field, or forcing pointer semantics on the input. There's nothing stopping you from doing that. You may even have to when, again, a value can't be copied. Now, look at what happens, though, when I do that to this implementation. It could be potentially confusing to the user. Now the add method is asking for a pointer of type user. Now it's asking for a pointer to a pointer of type user. Makes sense, right? Because in the first case, when we pass user here, this becomes user. It's not this anymore. It's this. And when we pass this, now this became that. Same thing on this side. So I want you to be aware from a usability standpoint that if both value and pointer semantics are safe to use in an implementation, then don't play with T. Let the user define T for what they need it to be, what data semantic they want to work in, and then the rest of the API follows suit. But if you do know that this is dangerous, where if they specify user and it's dangerous, then yeah, you're going to have to go in and you're going to have to try to be very clear that your API isn't matching what you're using for T during construction. Just want you to be aware of that, okay? Aware of that. That's tripped me up in some cases while I was learning. Okay, this is brilliant. It is 3:07. I promised I'd be done at around 3:15. I'm probably about 7 minutes behind. I hope that's okay with everyone. But there's 2 more examples that I need to share to give you, again, that 80–85% of what the draft is really trying to provide. And these last 2 examples are very, very important because they focus on another aspect of this that's critically important, and that's constraint. Up to this point, these 3 examples that I've provided, T was able to be substituted for anything because there was no real constraint on the implementation of code against T. But that's not necessarily realistic. There are going to be times where T has to be constrained because the implementation of a function, let's say, won't support all types. And I want to share 2 examples of that with you before I'm done here with this talk. Now, there's 2 types of constraints that are applied. The first one, and the one I'm going to talk about here, is behavioral constraint. And let's start with that. So I want you to look on line 13 and 22. You see I'm defining user-defined types. And in each one of these cases, for my user or my customer, I've added a method named string that returns a string. What these methods essentially do is stringify their related entity. Line 18, we're stringifying a user. On line 27, we're stringifying a customer. I'm using a JSON syntax, but why would I ever want to do this? Maybe I want to log these particular data values, and by being able to stringify them, I can control how they are written to a log. Now, to make this example a little bit more interesting, I've written these stringify functions that can do stringification in a bulk. So the first one says stringify users, right? It's a concrete function. It accepts a slice of user, and that's it. And then it returns a slice of string where we can match the same index position and have the stringification. And you can see the 5 lines of code. We construct the slice of string for the return. We can use the built-in function len to determine the length. We then go ahead and really the capacity, sorry. We go ahead and then we do a linear traversal, each user at a time, using append to add a new user to the new slice. And the key here is that we have to call string because string has the intelligence that we built in to do the stringification. Then we can return it. And those 5 lines of code are essentially the same 5 lines of code you see for stringify customer. We've just changed the variable names, and that's it. It's the same 5 lines of code. It's the same problem that we started with, right? And the thing here is that that string method is the key to all of it. Now, very quickly, I'm not going to break this down. We've done it already. There it is again, using the empty interface and type assertions. I could consolidate this stuff, but once again, the lines of code are pretty much the same, right? We're not gaining a lot of value around this consolidation. This is interesting, though. With 13 lines of code, guess what I'm able to do? Yep, I'm able to write a generic version of my stringify function using the reflect package. But we just went from 5 lines of code to 13. We walked away from our language syntax and mechanics to an API. And I'm sorry, but every time I look at this code and I wrote it, it's not obvious to me just by staring at it. I have to break it down every single time, right? Empty interface to accept any data of any type. Reflect over it. Is it a slice? If not, return nil. Construct the new slice of string to the right capacity using the built-in method len, not the built-in function, but the method len. Again, we can't use for range mechanics, increment I over length. Now this is cool. For every value that we index over, I can ask a question at runtime. Does that value have a method named string? Awesome. Now if it doesn't, I'm done, can't do much. But if it does, I can call it. And then we can take that value and get it into the append call. So guess what? I'm able to actually, through reflection, execute a method at runtime if it exists. Pretty cool. But let's agree, this code is not easy to read. You know, there's a higher bar of entry in comprehending what this does. We do have a single function in terms of maintenance, but I mean, even maintaining this code, we could easily break something if we're not careful. So let's go look at generics, because I think generics gives us everything we want here. And I'm going to pull this out again and start from where we're at. So here it is. There's that stringify function. It's going to be our generic function. Once again, you can see that this function is asking for a slice of some type t. Remember, generic functions are really concrete functions. And we're asking for a slice of some type t, but not a t that's going to exist and be declared, but a t that represents a generic type. And in this case, like I've been doing all during the talk, I'll just say any. A generic type t to be determined later that at least right now can be anything. And here are the same 5 lines of code that I wrote before that we started with that have the higher level of readability and comprehension because we're using language syntax and semantics. Now, I do have a main application here that will call into it. That's not important. What's important is I want to go ahead and build and run this code. Notice I have a compiler message on line 114. It's talking about the call to string being undefined. Here's a situation where we expect any value of type t, that's what this value is, it's a value of type t to be determined later. We're expecting that this piece of data of type t have a method named string. But we haven't given the compiler the information that this constraint needs to exist. We've told the compiler that t can be anything, but obviously it can't be anything. Because if that data doesn't know how to string, well, this function has no integrity. It's going to panic. Now let me explore something with you real quick here. I can write a function like this, right? I've defined user. I can write a function like this. I called this a concrete function, right? Because this function is asking for data based on what it is. This function works with user values and only user values. Doesn't work with our customer values, only our user values. It's a concrete function. But I could also write Bill. If I could spell today. Like this. This is a polymorphic function. This function is using the fumped.stringer interface. This function is not asking for data based on what it is. It's asking for data based on what it can do. What this function is saying is I will accept any concrete piece of data as long as it implements the full method set of behavior defined by stringer. The interface is applying a behavioral constraint to what data can be passed into this function at runtime. And because we're using a behavioral constraint, because we're using polymorphism, that means I can pass both user and customer values into this function because they both implement a method named string, which satisfies the stringer interface. And it's polymorphic because line 15 changes its behavior depending upon the concrete data we're operating on. So if I pass in a user value, we'll see the stringification of a user. If I pass in a customer value, line 115 changes because now we see the stringification of a customer. That's what makes this polymorphic. Polymorphism means that a piece of code changes its behavior depending upon the concrete data it is operating on. This is the polymorphism we have today in Go. We do it through the use of the interface. The interface defines a method set of behavior, which really defines a constraint that data must exhibit in order for it to be passed and flow through this function. And the compiler is able to, at compile time, validate that the data we plan to pass across that program boundary does exhibit that full method set of behavior. In other words, the language already has the concept of behavioral constraint through the use of an interface. When we look at our generic functions, which are concrete functions, however, they're special concrete functions, right? Because we're going to be able to, at compile time, substitute what t is. This is considered, in many cases, also polymorphic, right? It's compiler time polymorphism because this code can change its behavior depending upon the data that we pass in based on the type that we use to implement that particular function. It's polymorphism, but it's a different type of polymorphism. But nonetheless, T can only be substituted for types where data of that type can exhibit this behavior. We have the same kind of problem. We have to apply a behavioral constraint. So the draft says, look, we're already using interfaces today to declare behavioral constraints for polymorphic functions. This is technically a polymorphic function as well, though it's compile time. Why not reuse the interface to apply the constraints we need on the data that eventually we pass in here so the compiler can validate that this method will exist? And that's exactly what the draft is doing. So I'm going to replace any with func.stringer. And now this code compiles and runs because we've now provided the compiler with the proper constraint that is required for that substitution of t. Pretty cool, okay? Pretty cool. So we're reusing the interface for our traditional polymorphic functions, and now for our generic functions to apply that behavioral constraint. And it works, and I like this. And it just seems right. OK, there's one more thing I have to show you. I promise I'm going to make it quick. And it's because generic functions actually bring to it another type of constraint that we don't currently have in the language. This is what I could call an operational constraint. See, our generic functions are substituting t for types. But there are certain operations that a function might be applying to data that really doesn't come up in our traditional polymorphic functions, but will absolutely come up in our generic functions. Let me give you an example of what I mean. Let's remove the generic information, generic type declaration for a second. You know what I want to do on line 16. You know it at this point, right? I want to write a function named add that can take a value of some type t and a second value of the same type t, add those two values together and return a new value of type t. So we know t is a generic type, right? So we might come in and do this like I've been doing. But that's a problem because I can't say that t can be anything, right? Because look, even though t can be an int, and t could be a string, can t be a user? Can t be a struct type user? No. We can't add two user values together in this language. We don't have concepts of operator overloading. I don't expect that we ever will, at least not in a major version 1 of Go. And so T can't be anything. In fact, we can even make an argument that if that's a string, that can't even now work either, because you can't subtract two strings. So you see where I'm going, right? This operation requires a constraint on T, because not all data values of a given type can be used in an add, subtract, divide, you get it, operation. But this is weird. This is a problem, because this isn't necessarily a behavioral constraint, right? It's not like I could define an interface with a method set, again, because we don't have any operator overloading, and suddenly this would work. This is brand new. This is a new problem. We need some new syntax. But I don't want to define a new type for this type of constraint. I want to keep things consistent. And so what the draft has come up with to this point is this idea right here. Now, what this idea says is the following. We are using interfaces today to define constraints. I mean, so be it behavioral constraints, but nonetheless, constraints on what data can be. And we'd like to continue to use the interface to define constraints. But this isn't a behavioral constraint now. It really is a concrete constraint, right? It's what the concrete data can be in a particular subset of types. And so the idea here is that on line 13, we define an interface which represents a list of types that, in this case, T can be. And so we won't say any. We'll say add only. And now what we're telling the compiler is if anyone tries to call add, and the data they're passing in for T isn't a type in this list, no good. And this supports underlying types, by the way. So I could pass bills around, which is good because then it crosses over package boundaries. If you put your user-defined types in here, well, right, you can't extend that across package boundaries, so that's interesting. There's another interesting kind of caveat to this. We can't write traditional polymorphic functions with these interfaces because there's no method set of behavior defined. So we suddenly now, with this syntax, have a set of interfaces that can only be used with our generic functions, or can only be used around our generic functions. We can't use them in our traditional polymorphic functions because they just don't define a method set of behavior, right? And these functions here are all about that polymorphism. So that is interesting. But over the last few months, there have been a lot of discussions on the mailing list and other places about this. And there just hasn't been a better idea, at least one that I have seen. Now, understand something here. Only one constraint can be applied to a given type. And if you have a list of types, you can just define the one constraint that would be applied to all. Or you can individually, do things like this. But at the end of the day, only one constraint can be applied. You can't have a list of constraints. So that creates some restriction in the fact that, let's say, and I have not found a practical reason for this, if somebody ever does, I want to see it. But this does give you the ability to find an interface that would have both a type constraint and a behavioral constraint. Now, once again, I have not found at any level the need for this, how that would apply, because normally if you have behavioral constraint, things like adding or something would be done almost here, where in that case you might say, right, you might do something where add takes a T and a T and then returns a T or something, right? And then you would use add behavior here, and you wouldn't need this anymore because you're going to do it through a polymorphic way where you're going to do it through behavior, right? And so I haven't seen a situation yet where it makes sense to have both a type list and a method, or even this situation where we have a substitution of a generic type to do it either. I just haven't seen it yet. I'd love to find one, because maybe if we don't, then it doesn't really matter that we're doing this. Now, one of the ideas, though, to help is to either create a set of other predefined constraints. One of them that we have already today is comparable. So if you're going to be writing generic functions, they're going to be doing that sort of statement, comparing. You don't have to write your own comparable interface. And I expect that the standard library will probably have a package of these interfaces that are going to be very common for a lot of these types of constraints, so we don't have to write them all. There's other code in this example that is interesting, but because of time, I'm going to skip it. Eric, come back to me, please. OK. So that's my hour and 15 minutes. I apologize. But we got through a good 80–85% of the draft. You saw in that very last example where things maybe are getting a little interesting because we need a new syntax or something we really don't have. You kind of see where we're settling out right now. And I haven't seen any new discussions around that or anything that's even better. Now, with that being said, now is a good time where I want to go through and give everybody an opportunity to either ask a question or I'd like to hear everybody's thoughts. I did see some questions while I was talking. I can answer those real quick. Michael asked about the any and if it's going to be an alias to an interface and can it be used outside of generics. The answer is it will not be allowed to be used outside of generics. That was the initial idea. And then everybody started complaining because we didn't want to see any everywhere. And so any's going to be restricted to just being a constraint. But any does alias, or however they're going to end up doing it, it's the empty interface pretty much at the end of the day. Can you have two types, vector and a vector t? I don't think so, Adam. I haven't tried it in the new syntax, but I doubt that you can define a vector and then a vector of some generic type. I haven't tried it. I would be shocked if you could, though, to be honest with you. Adam?
Later when you demonstrated later on that it wouldn't work because as soon as the compiler can interpret type, then you would have vector and it would work it out and so it would collide. So it wouldn't work.
Yeah, it would. With the, you're right. With the literal construction, there'd be ambiguity there, wouldn't there? You're right. So perfect. And then Adam, you had a thought. So Adam, why don't I start with you? I'd love to hear your thoughts. You can talk about your thoughts on that zero value. And then if you have any other questions too, I'd be more than glad to answer them. But take like 2 or 3 minutes.
No, I liked it. It's obviously difficult to pitch because in terms of how much you cover in terms of generics as a concept. I'm from like a C and C# background, so a lot of the stuff was kind of it's interesting to see how it goes. It's kind of there's always going to be that difference in different experiences. So that's a problem that you obviously have to solve every single time. So it was good though. I liked it. The zero value thing, that's just bike shedding. It's kind of like over 3 lines of code. Who cares? It's you move it closer, it might look worse. It's 3 lines, you can't tell. It's on a bigger function, it might make a difference, But yeah, thanks.
Brilliant, brilliant. All right, the next person in this list is Jessel. If I'm saying your name wrong, please correct me. I'm horrible at names. But Jessel, do you have anything you'd like to share? Any questions or any comments about what you saw? You don't have to. Can we add multiple interfaces in Funct Stringer example? If you're talking about the, Eric, come back to my code here. if you're talking about, you can't have a list of interfaces here, all right? You can only apply one. So if you needed that extra behavior defined, you'd have to use composition, right? You'd have to say, I'm going to declare the bill interface, and the bill interface is going to be everything that the stringer is, plus we're going to handle a match or something, right? Doing that right. And then you can apply bill here. So you can't have multiple interfaces in that list. It's one constraint per type. And so it becomes important then to be leveraging composition. I hope that answers your question on that one. Okay. And all right, perfect. So Usman, do you have anything you'd like to share with what you saw, thoughts, opinions, questions? Eric, come back to me.
No, it was an excellent talk. Really clear example. I like that.
All right, brilliant. Paulio, you got anything you'd like to add, share, thoughts, opinions, questions? Okay. All right, that's fair. Vlastimil, if I'm saying that wrong, I apologize. Do you have anything you'd like to share, add, thoughts, opinions, questions?
No, I think it's really good. I really enjoyed it.
All right, brilliant. Alan.
No, I'm good.
All right, and Emin. Nothing from Emin. That's fair. Michael, I'm leaving you last there. So do you have anything you want to add, share, questions on some of the things that we talked about here in this talk?
Not directly. I was surprised how many details you have to get right. It was a lot more fuzzy than expected. When you think, yeah, let's just add generics, right? Everybody, Python has it, right? So that was a really good talk. Thanks.
Yeah, so this is why Ian's been working on this for about 10 years. And Eric, come back to my machine for a second. If you want to get a little bit more academic, I mean, I definitely suggest that you read the draft. But there's this link. I'm going to give it to Eric here. Eric, Eric, come off my screen for a second. Come off my screen. I'm going to drop this link so you can drop it. And then Eric, drop those other 3 links again into the chat for me. But yeah, come back to my screen now. So if you want to get a little more academic, Ian and Robert, you see them in the top of this document here. They worked on this, and a lot of the work that was done on this document came back to making those changes to this new draft release, like the use of interfaces and the way they're being used. I have not read this yet. It's on my list. This is kind of like academic stuff, so I have a harder time consuming that stuff, so I need to really kind of sit back. But if you're more into the academic side of this as well, then this is a really interesting paper that I think you'll enjoy. Okay, Eric, come back to me. There is going to be a recording once it's available from Zoom. I think Michael's going to put it up on a YouTube channel or something. I at Ardan, we recorded this thing, recorded this talk also.
My name is Bill Kennedy. And
dude, what are you doing? No, I also, I don't know where that came from. We'll be publishing this too in the Ardan Labs YouTube as well, but it will be there for sure. All right. That's all I've got. I really appreciate everybody's time. Eric, drop my email in there too, please. If you have any other questions or thoughts, you want to share anything with me, Eric's dropping my email address there. Just do that. You can find me on Twitter, on Slack, whatever you need. And that's it. Back to you, Michael.
Bill, thanks very much. Yeah, I can see why you're a professional trainer. It's always excellent. for everybody else, we don't have a next meetup scheduled yet, so if anybody wants to give a talk, maybe about generics as well, please let us, let either Adam or me know, and then we'll book something in for about either next month or the month after. Thank you very much.
Cool.